Okay, this is the y component of velocity. This is the x component of velocity. And this is the angle theta. And I should have labeled the axes, but it's clear, it's always the same. Okay. Now, let's write down the velocity v. Equals minus v sine theta in the I direction plus v cosine theta in the j direction. So that angle is theta. That makes this angle right here theta. This angle is 90 minus theta. And the x component, its magnitude is going to be given by v, the magnitude of this vector here, times the cosine of 90 minus theta, which is the sine of theta. And it's in the negative direction. Vy, well, if that's 90 minus theta, then Vy is going to be V, and it's in the positive direction, V times the sine of 90 minus theta, which is V times the cosine of theta. Okay. Now, that equals minus V. Now, what is the sine? The sine is, if this point right here has coordinates x and y, the sine of theta is just y over r. Okay, now we want the acceleration. This v is the magnitude of the velocity, so it's a constant. R is a constant because the motion is circular. So let's write down the equation for A. A is equal to dvx dt times I plus dvy dt times j, and that is equal to, now look at this term right here. We want to differentiate this term with respect to t. So we've got v is a constant and r is a constant. So the only thing that's not a constant is the y coordinate. And what is dy dt? Dy dt is the y component of velocity. So the acceleration equals minus v over r v sub y times I plus v over r v sub x in the j direction. But what is v sub y? From up here, v sub y is v x over r, or v cosine theta. So this becomes minus v squared cosine theta over r plus v squared sine theta over r. And this is in the I direction, and this is in the j direction, because Vx is equal to Vy over r, or V sine theta. Okay, now this is the acceleration, which is a vector. In this particular problem of uniform circular motion, the acceleration is always towards the center. How do I know that? The speed is not changing. Therefore, the acceleration only has a perpendicular component, and the direction perpendicular to the motion at every point is towards the center. So this is called centripetal acceleration. And centripetal acceleration does not change the speed, but changes the direction. So whatever is causing this thing to move in a circle, maybe we've tied it up to a piece of string and it's moving around on a circle whose radius is the length of the string. Whatever is causing that is pulling it towards the center. So that's centripetal acceleration. And the acceleration as a vector changes continuously, but its magnitude is always a constant. Just like V has a constant magnitude, even though its direction is constantly changing as it moves around, the acceleration A has a constant magnitude, even though its direction is changing as it moves around. And what is the magnitude of the acceleration? Well, that's easy. It's the square root of a sub x squared plus a sub y squared, which is equal to the square root of, now we've got v to the fourth over r squared cosine squared theta plus v to the fourth over r squared sine squared theta. I can factor out the v to the fourth over r squared, and what is the cosine squared plus the sine squared?
1.
2n? Okay, that's fine. Yes, it's equal to 1. So that means this is just the square root of v to the fourth over r squared. In other words, it's v squared over r. So in uniform circular motion, the magnitude of the acceleration is v squared over r, and it is always pointed at the center. Now, what if it's moving around a circle of constant radius, but it's speeding up as it moves? In that case, the motion is no longer uniform circular motion, but the acceleration is always pointed towards the centripetal portion of the acceleration is pointed towards the center, and there's a parallel component of acceleration causing it to speed up as it goes around. And the magnitude of the acceleration, being v squared over r, will actually change as the speed of the particle changes. But in this case, in uniform circular motion, the speed is constant, so the magnitude of acceleration is constant as well. Okay. This is really important. The magnitude of centripetal acceleration equals v squared over r for circular motion. So that's something you're going to use over and over again throughout the whole semester. All right, our last subject. Well, are there any questions?
Oh yeah, one real quick.
Is this from from
3.
chapter 3?
Yes.
Okay.
So we're way ahead of schedule. All right, now, why are we so far ahead of schedule? Because I put lots of time into the schedule for you to ask questions about the homework problems or any other problems. So you must read ahead of time and prepare questions and work the problems ahead of time and prepare questions. Because otherwise, we're just going to get through with the lecture for the whole semester in half a semester, and you're going to be completely lost. So please read ahead and work the problems ahead. And don't be bashful about asking questions. I always say, are there any questions? But that doesn't mean that you have to wait for me to say that. You can raise your hand or you can just speak up. You can always ask questions. All right.
I have a question now.
Go ahead.
So then it seems like today we're working on chapter 3 and then we'll be moving on to chapter 4. So are you saying that by next class it'd be ideal if we have read chapter 4 and started working on the problems and kind of have already finished chapter 3?
Yes. Move ahead by all means. By all means, read ahead and work on something. Have you done all problem chapter 3 yet?
No. I need to get.
Have you done all problem chapter 2 yet?
I'm finishing up.
Okay. All right. And you didn't have any questions on chapter 2 problems?
I did. I had a couple questions at the beginning of class.
Okay. All right. I mean, you have more questions now.
No.
Okay. All right. Good. Okay. Well, everybody needs to do what you're doing then. Okay. Let's move on to the last subject for chapter 3. And that's relative motion. Now, relative motion tends to be confusing. And the reason that it tends to be confusing is that people kind of like to solve a problem in their head without formally setting it up. So let's set it up formally. And then let's say that you have for one-dimensional motion. We have a reference frame A. And this reference frame A is fixed with respect to the observer. There is another reference frame B, and I'm drawing this as a two-dimensional frame, but it's a one-dimensional problem. This reference frame B is moving with respect to A with the speed V of B with respect to A. That's what VA means. The velocity, and it is a velocity because this can be generalized to multiple dimensions. It's a one-dimensional problem now, but VA is velocity of B with respect to A. So B is moving along the x-axis of A with some speed VBA, and VBA is a constant speed. Okay. Now there's some particle that, as measured from reference frame B, has a speed V of the particle with respect to B. And we would like to know what is V of the particle with respect to A as measured in the A frame. This is called the standard configuration, and you will see this in relativity. So next semester, I think Professor G is offering a course called Relativity for Poets. And if you take that, you will see this standard configuration. All right, let's define some more terms. this here represents the value x of B in A. So that's that point right there. As measured in frame A, that is the position of the origin of frame B at some time. And this is the position X of the particle measured in frame B. This point on the A-axis is X of the particle measured in frame A. Now, looking at this, it's obvious that the position X of the particle measured in frame A is just the position of the origin of B with respect to A, plus the position of the particle with respect to B. So positions are easy. Now, what about the velocities? Well, differentiate this all the way through with respect to time. And what you will end up with is the velocity of P in A is equal to the velocity of B in A plus the velocity of the particle in B. So if B is moving at, let's just do a numerical example, 2 meters per second, and as measured in B, the speed of the particle is 3 meters per second, then, Michelle, what will be the velocity of P as measured in A?
Could you say the question again, or like maybe rephrase it in a sense?
Okay, well, I'll say it again. B, this reference frame, is moving to the right at 2 meters per second. Within B, if I were moving with B, I would measure the speed of the particle at 3 meters per second. So if I stand in A and watch the particle go by, what is the speed of the particle as seen from A?
So would you add B and A and then, so would it be 5?
It would be 5.
Okay.
Okay, common sense kind of tells you it's going to be 5. This is sort of easy to see. That if, think of it as a moving walkway. So I'm in the airport, there's a moving walkway, and the walkway is moving to the right, and it's moving to the right with 2 meters per second. The person on the walkway is walking at 3 meters per second. Boy, that's fast. 3 meters, he's running 3 meters per second as measured in the walkway frame. I see him going by at 5 meters per second, because his velocity is added to the velocity of the moving walkway. And that's what this equation says, doesn't it? The velocity of the particle as measured in A is the velocity of B as measured in A, plus the velocity of the particle as measured in B. And I've written this as a one-dimensional equation, but in fact, it can be generalized to 3 dimensions by simply saying, well, these things are vectors. They have X, Y, and Z components. Now, V of B with respect to A is a constant. So what can I say about the acceleration of the particle here? Now, VBA is a constant, right? So if I differentiate this all the way through, I'll get the acceleration of the particle as measured in A equals 0 because B is not accelerating, plus the acceleration of the particle in B. So these two frames are what is called inertial reference frames. And an inertial reference frame is a frame that is moving with a constant velocity with respect to another inertial frame. So I'm considering A to be at rest. B is moving with a constant velocity with respect to A. So B is an inertial frame because I consider A to be an inertial frame. And go ahead.
Yeah, I have a question. So then what you're saying is that reference frame A and B have the same velocity, which is why B does not have an acceleration with respect to A's reference frame?
No, A is at rest and
Oh.
B is moving. So if I have a moving walkway in an airport, the airport is frame A and the walkway is moving with respect to frame A. Because the airport's still, it's not moving, but the walkway is moving. But the walkway moves with a constant velocity with respect to A.
Mm-hmm. Okay.
Okay.
Yeah.
Now, these are what are called inertial reference frames. And the velocities and positions have different values, although they're all consistent because the physics is the same. Physics does not depend on your reference frame. But the accelerations are the same in both frames. So I may see from frame A, my particle is moving faster with respect to me than it is with respect to someone fixed to frame B. But the rate of change of those velocities is the same because VBA is a constant. So the accelerations are the same. And we will learn in chapter 4 that because the accelerations are the same, the forces are the same. So Newton's second law, just to give you a preview, is F equals ma. This is true only in an inertial frame of reference. Now, you may have tripped to the logical inconsistency in all this. What is it? Does anyone have an idea? B is inertial because it's moving with a constant velocity with respect to A. How do I know that A is inertial? That's the question. Andreas, what do you think? How do I know that A is inertial?
That's a tough one.
Well, let me give you the definition. An inertial reference frame has a constant velocity with respect to another inertial frame. So B is inertial because it's moving with constant velocity with respect to A. A is inertial because
B is moving?
No. Because it must be moving with a constant velocity with respect to some other reference frame that's inertial. Well, how do I know that other reference frame is inertial? So you see, it just keeps going back forever. So, so Newton, of course, thought of this, and he reasoned thusly. The background of the distant stars is not moving with respect to the Earth. And he is hypothesizing that the background of the distant stars is not moving at all. is fixed, not moving with respect to the rest of the universe. So, so any frame which is moving with a constant velocity with respect to the background of the most distant stars is an inertial frame, because the frame containing the most distant stars is an inertial frame by his hypothesis. Well, that sounds perfectly reasonable, because the Earth spins and it goes around the sun, and because of that, it appears as if the background of the stars is moving around the Earth, but they're all kind of moving together, aren't they? I mean, the shape of the constellations doesn't change. Well, it does over sufficiently long periods of time. But for short periods of time, human lifetimes, or even thousands of years, they don't. So it's completely reasonable to take that as an inertial, as a preferred inertial frame. However, that's not the modern view. The modern view is that there is no preferred inertial frame, and that you can tell if you're in an inertial frame, because if the frame you're in is not inertial, you will experience things that seem unphysical. For example, let's say that we take the Earth to be an inertial frame. It is not, strictly speaking, because the Earth is spinning and it's also moving around the sun. But for practical purposes in the laboratory, we can take the Earth to be an inertial frame. So if I'm driving in a car, I'm a passenger, let's say, and the car makes a left-hand turn, I feel like something is pushing me into the door. So what's pushing me into the door? The driver's not pushing me. There's nobody there pushing me. It's completely mysterious. Why do I feel like I'm being pushed into the door when there is nothing pushing me? And the answer is, you're in a non-inertial frame. Let's say that you're in an elevator, and the elevator is accelerating upwards. You can feel yourself being pushed into the floor, can't you? If you stood on a scale, it would register a weight greater than your actual weight. But what's pushing you? Nothing's pushing you. That must mean you're in a non-inertial frame. So the modern view is that there is no preferred inertial frame, and that an inertial frame is one in which, by definition, F equals ma. So Newton's laws of dynamics hold in inertial frames. Now, what do I mean by hold? I mean that if I measure A in that frame and I measure F, then it makes sense, okay? Think about the elevator accelerating upward. So here's the elevator, I'm accelerating upward, and I feel myself being pushed down into the ground, okay? Well, in the frame of the elevator, I am not accelerating, am I? I'm not moving with respect to the elevator. So I have no acceleration. So that is zero, yet I feel a force. That's what I mean by the laws of dynamics fail in a non-inertial frame. F equals ma fails in a non-inertial frame. That's what I mean. Okay. So that's your introduction to inertial reference frames and relative motion. There's a PIP problem in chapter 3, I think, PIP, that is a moving walkway in an airport. And it has multiple parts. The first one or two parts are simple. You can just sort of reason with a little picture in your head what's going on. But for the other parts of the question, it's going to be very confusing. So what you should do is you should draw the standard configuration, draw this, and assign to reference frame, assign the various things in the problem to reference frame A, reference frame B, and the particle. So a person walking on the walkway in the airport, well, the airport could be frame A. The person on the walkway could be frame B. And the person on the walkway is like a particle in frame B that's moving with respect to frame B and frame A. But you might have it the other way around. You might say that the walkway is frame A, in which case frame B would be the airport moving not to the right, but to the left. So when you solve these kinds of problems with relative motion, go ahead and make yourself a diagram of the standard configuration and assign meaning to the reference frames and the particle. And that will help you figure out the problem. And of course, these are your two equations for relative motion. Oh, and this one, of course, but you're not going to need this one. All right. Does anybody have a question on relative motion? All right. Well, I'm going to let you go. You've got a little over half an hour left in class, but I'm going to let you go. So what are you going to do with that half hour? Chapter 2 PIP and Chapter 2 MP is due tonight. So you got an extra half hour to work on them. And if you're done, you should begin work on the problems in Chapter 3 if you haven't already. And please read the book. Here's a trick that I use when I study. Let's say I'm reading Chapter 3 and I have sections 3.1, 3.2, 3.3. And I have problems in the back that are associated with those sections. So read 3.1 and work the problems in 3.1. Then read 3.2 and work the problems in 3.2. That way, your mind has a break from just reading, but you really hammer down the concepts and ideas of that section by working the problems. And because of that, when you go to read section 3.2, you're going to understand it better, and so on. All right, so I'll get off my soapbox. Anybody have anything they want to say?
Yeah, I do. Well, I mean, I don't know if you could go over it quickly, but it was, I believe, the second example you gave, or you talked about, which was the problem you gave us last week, and specifically just about the AX and the AY component. Yes, there you go.
Okay,
And I was just,
go ahead.
yeah, so for the AX and the AY component, well, obviously there's the sine theta and cosine theta, and I have an idea of why it's there, but a better explanation would it be that you kind of use the Pythagorean theorem, and then you do like the sine theta is equal to like the opposite over the
Yeah.
hypotenuse, and then
That's exactly where it comes from.
Oh,
That's
that's
exactly what I did. I did it in my head, but I
Okay.
did that. You're exactly right.
Oh, okay, yeah. Could you just write out the AX and the Y component like on the diagram so I could maybe visualize it and just kind of solve it like that?
Okay, so this G is the acceleration vector.
Okay.
This piece right here is A sub X. Okay,
Oh,
this is 90 minus theta, and this is theta. So what is this length A sub X? Well, the sine of theta is A sub X over G. Therefore, A sub X is G sine theta.
yes, that's what yeah, okay. I kind of knew something like that, but I couldn't remember exactly how it was, but now, And then
Good.
that makes sense. And then you would kind of just use that method for other,
Yes.
right?
Yeah, you'll be doing this so much it'll become second nature. This piece right here, this length, is a sub y. Well, its length, a sub y over g, is equal to the cosine of theta. So that means the magnitude of a sub y is g cosine theta. However, it is in the negative y direction. So you have to put the negative sign ad hoc there.
Mhm.
You'll get used to the idea that the projection of a vector onto an axis is the magnitude of that vector times the cosine of the angle between the two.
Mhm. Okay. Got it. And then for the Vx and the Vy,
Those are kinematic equations.
kinematic equation, then how do the cosine theta and the sine theta fit in?
Well,
Or I guess I see the acceleration component for the last part of it, but as far as the V and V naught cosine theta, where does that the cosine theta come from?
okay. Well, I'm going to draw it in purple. Here's my V0. That's my V0 vector.
Mm-hmm.
Its projection on the y-axis is here, and its projection on the x-axis is here. So V0y is this distance, and this distance right here is V0x. Now, what are they, given the angle theta? Well, this angle right here is 90 minus theta, which means that that angle right there is theta. So you can do it in terms of theta or in terms of 90 minus theta.
Mm-hmm. Okay.
Okay?
Yep, I got it. All right, thank you,
Good.
Professor.
Okay, well, Sophia, if you're still here, I'm sorry you're having trouble with your internet. Hope you get it fixed. And I hope everyone has a really good weekend and a really good Labor Day. You've got a lot of time to work on chapter 3, and 4. So get working and have a good one.